Okay, let's unpack this.
Let's do it.
We have spent, the last few years just watching these massive language models, the chatbots, all the assistants, completely explode in power.
Right.
They've gone from, simple text generators to systems that can ace professional exams, write incredibly complex code.
And synthesize thousands of documents in seconds.
Exactly. It's this AI revolution happening entirely in the digital world, in the cloud.
Mm-hmm.
But there has always been this nagging foundational question.
Mm-hmm.
And it's a question that engineers at Google have apparently spent 7 years and, billions of dollars trying to answer. What happens when a massive language model tries to get a robot body?
It's the ultimate reality check for AI. And, frankly, for our own understanding of what intelligence even is.
Right.
We call it the embodiment challenge. And the gap between that cutting-edge AI reasoning and, writing a 10,000-word essay on astrophysics.
Yeah, the stuff that seems impossibly hard.
Exactly. The gap between that and reliable, general-purpose, real-world robot action remains, well, it's surprisingly wide.
That's the core paradox, isn't it?
Mm.
It always gets me when you look at robotics progress versus, say, software progress.
Mm-hmm.
Why is asking an LLM to plan a lunar colonization mission, something that sounds like science fiction, seemingly easier than asking a pretty sophisticated robot to just reliably pick up a sticky cup from a messy desk?
It feels completely backward.
It does. It feels like the concrete should be easier than the abstract.
But the difference, it really just boils down to two things: data and physics.
Okay.
These high-level cognitive models, your Geminis, your GPT-4s, they operate in a perfect digital space.
Right. The internet.
The internet, all that data is abundant, it's clean, searchable, and it's static. They've consumed basically every piece of text and code ever created.
So they have this incredible knowledge.
Incredible semantic knowledge and reasoning power. But they exist in a vacuum. To be useful in our world, in the physical world, they desperately need real-world data to anchor all that knowledge in physics, in friction, unexpected collisions, just the chaos of reality.
So an LLM knows what a cup is, it knows what stickiness is, it knows what a desk is conceptually.
Yes.
But it has no sort of intuitive physical model for exactly how much torque it needs to pull that sticky cup free without, knocking over the monitor right next to it.
Exactly. Without that physical anchor, the LLM is just a theoretical planner. It hits edge cases immediately, the cup is wet, the surface is a little slanted, the lighting changed.
All the things we don't even think about.
And that's why Google DeepMind and its precursor teams have spent the better part of a decade trying to bridge that exact chasm. And they've learned some extremely hard, very expensive lessons along the way.
So let's dive into those hard lessons. That brings us to the first major phase of Google's mission, and this attempt started way back in 2016.
Right, within Google's Alphabet division, specifically X, the sort of secret innovation lab.
The Moonshot Factory.
That's the one. The project was initially called Everyday Robotics, and then later just Everyday Robots. And they had a truly, truly audacious goal.
Which was what?
The mission was, it was deeply personal to Google's founder, Larry Page. He wanted to create AI-powered robots that could flexibly help humans with any task in a totally unstructured environment.
Like a helpful roommate or something.
Or a colleague, yeah.
Right.
And Page was a big believer in moving directly to what they called end-to-end learning, or E2E.
Okay, and E2E learning, in this context, that was sort of the holy grail, right? A single massive model that takes in raw sensor data and then just spits out motor commands without all the old school hand-coded steps in between.
Precisely. It meant you could give the robot a really general high-level task. Something like, hey, can you tidy up the conference room for the 3 p.m. meeting?
And the AI just figures it out.
It figures out all the complex sub-actions. Identify the clutter, recognize that the whiteboard is dirty, plan the best path around the chairs, and then execute the exact motion needed to wipe the marker off.
So the AI builds its intelligence organically, kind of like a child learning through trial and error.
That was the goal. A true moonshot investment.
Mm-hmm.
It needed massive capital and, a lot of patience.
But the project, even after 7 years of work and a huge investment, it was effectively shut down in February 2023.
It was.
And this was the moment the whole industry really had to face the reality of this data problem. So what was it? What fundamentally was the central point of failure?
The central failure, and we know this from some detailed reflections by Hans-Peter Bronmo, who was the former CEO of Everyday Robotics,
Okay.
he said it was the sheer scale and speed of the data bottleneck in the physical world. The whole vision of generalized E2E learning, where the robot just figures it all out from a simple prompt, it proved to be structurally out of reach
Why? Because of physics.
because of friction, gravity, material physics, all of it.
Can we put a number on that? I mean, LLMs are ingesting trillions of tokens of data. How does that even compare to what a robot can do?
Oh, it's not even in the same universe. It's exponentially harder. Brano's conclusion from all that work was pretty sobering. He said to achieve true, generalized capabilities.
Meaning it can handle tasks it's never seen before.
Exactly. A novel item, a new environment. To do that, AI needs, and this is a quote, many, many thousands, maybe even millions of robots doing stuff in the real world to collect enough data.
Millions of robots.
Think about that gap. To collect 1 hour of perfect, labeled, high-fidelity physical data requires immense effort, calibration, safety checks. Meanwhile, collecting trillions of digital tokens is just a matter of scraping the internet.
So the robot is learning at this, like linear physical rate bound by the speed of light and how fast its joints can move, while the LLM is learning at this exponential digital rate bound only by computing power. You could never close that gap.
Yeah, that's the core tension. Physical data collection is just inherently slow. It's incredibly costly to scale up. And critically, it lacks the huge visual and linguistic diversity you need for robust generalization.
What do you mean by that?
Well, if you train a robot to pick up a blue block on a white table, it will often fail completely if the block is red, or the table is made of wood, or the lighting in the room changes.
Unless you've trained it on millions of different blocks and tables and lighting conditions.
Which is exactly what you can't do physically, not at scale. And this whole realization, it led Bronmo to voice this concern about the whole ecosystem in Silicon Valley. He called it a patience problem.
Patience problem.
He did, and it's a really critical insight. He was worried that the dominant venture capital model, which, it prioritizes rapid short-term returns, aims for a minimum viable product in 18 months.
Right.
That model, combined with a general aversion to investing in complex, expensive hardware, it fundamentally undermines the long-term, decade-spanning patience you need to actually win the global race for embodied AI.
So wait, this implies the failure wasn't just technical, it was also economic.
I think that's precisely the implication.
The Everyday Robots team figured out the path forward, but that path was just too expensive and too slow for a company like Google or Alphabet to sustain, especially under its usual quarterly review structure.
That's a great way to put it. The technical solution E2E, learning from scratch, it just required a scale of investment and a time commitment that didn't align with Silicon Valley's expectations, especially once the generative AI revolution hit and showed everyone what could be done really fast with digital data.
So the lesson was you can't train intelligence from physical scratch. The data is just too scarce.
Irrefutable.
So, okay, the core mission failed, but the lessons were obviously invaluable. If they couldn't generate the intelligence organically from physical data, they had to, what, transfer the intelligence they already had?
That was the monumental strategic pivot. Instead of trying to teach robots all this semantic and cognitive intelligence using limited real-world actions, the new goal became transferring the massive existing knowledge of the foundational LLMs.
All the language, the common sense, the planning ability.
All of it. Transferring that into the robot's action space. This wasn't about growing a brain from physical action anymore. It was about grafting the powerful brain they already built onto the physical body and then making it bilingual.
Bilingual.
Fluent in language and fluent in motor control. And that fundamental shift, that leads us directly to the really sophisticated agentic architectures we're seeing today at DeepMind.
That pivot is fascinating because it's really the marriage of the biggest breakthrough in software, LLMs, with the absolute hardest problem in hardware, which is robotics.
Yes.
So if the old way was a bottleneck, what does this new approach actually look like? How did DeepMind learn from that whole everyday robots experience and pivot to what we now have, the Gemini Robotics 1.5 architecture?
They pivoted toward a very sophisticated decoupled system that basically compartmentalizes intelligence. The concept is actually pretty simple. Let the powerful LLM handle all the planning and the abstract reasoning, and then use specialized models to handle the immediate low-latency physical stuff.
Yeah, and the key tech that lets them do that translation is the Vision Language Action Model, the VLA.
That's the one. VLA models like Gemini Robotics or Figures Helix, they're becoming foundational.
Okay, so beyond the acronym, what is their actual function? Why are they so necessary?
A VLA's core job is to synthesize everything. It connects perception, what the robot sees through its cameras, with language, the instructions it's given, or the plan it generates
That
internally,
translates that into movement.
and translates that into physical control, the motor commands. But the critical innovation in DeepMind's current system, the Gemini Robotics 1.5 stack, is the decoupled architecture.
Why decouple it? Why can't one single massive model just handle everything? Which is what they wanted to do with E2E learning in the first place.
Because of a fundamental trade-off between complexity, latency, and reliability. It's a classic engineering problem.
Okay.
High-level reasoning, deciding, planning, checking external facts. That's computationally intensive. It's slow. The planner might take half a second, 500 milliseconds, to process information and decide the next big step.
Which is an eternity in the physical world.
It is. Reliable physical control, reacting to friction or an unexpected gust of wind, that requires sub-millisecond real-time responses. We're talking under 10 milliseconds. If you use that big, slow planner model for real-time control, the robot becomes clumsy, slow, and frankly, unsafe.
So decoupling lets them manage that conflict. You have a slow, smart brain and a fast, more specialized body.
Exactly. You have this two-part system. First, you have the planner.
The brain.
The high-level brain. It's often called the Gemini Robotics ER 1.5 model, where ER stands for embodied reasoning. This model orchestrates all the high-level stuff. It excels at multi-step planning, complex logical decisions, and it has state-of-the-art spatial understanding. This is where all that vast LLM knowledge gets used.
And the power of the LLM here isn't just about internal thought. It's about accessing the outside world, right? Something a traditional robot controller could never do.
That's where the power of modern LLMs really shines in embodiment. The planner is designed for what they call tool use.
Tool use.
It can natively call digital tools, like Google Search or APIs, to inform its physical actions. The classic example they use in the research really captures the scope of this.
The complex recycling task.
Yes. So imagine the robot is given this really complex, localized, multi-step instruction. Can you sort these objects into the correct compost, recycling, and trash bins based on local city ordinances?
That's really specific.
It is. The robot needs to identify the bins and the objects, that's perception, but the crucial step is realizing that to do the task correctly, it needs to use a digital tool, Google Search, to check the specific recycling rules for, say, San Francisco or Austin, to see which plastics are actually accepted there.
That is true cognitive generalization, driving a physical action. The robot is taking abstract, digital, legal knowledge and combining it with concrete physical manipulation.
Precisely. The planner handles that complex reasoning. It figures out the multi-step plan based on its digital search, and then it translates that plan into simpler natural language instructions, and it passes those down to the second model.
The executor.
The executor.
And this is where the rubber meets the road, the messy reality of movement and physics.
Correct. The executor, which is the VLA model component of Gemini Robotics 1.5, it's heavily optimized for low latency real-time motor commands. It's the action layer.
So it takes the instruction, put the plastic bottle in the blue bin.
And it converts that instruction into rapid, precise physical movements. It decomposes it into short, reliable motion segments, maybe taking 10 or 20 low-level control steps every single second.
This whole architecture, it seems designed to make the robot's process more transparent. It's almost like the robot has to have an inner monologue.
It does. And that is a concept DeepMind actively champions, thinking before acting. The Gemini Robotics 1.5 executor is trained not just to act, but to actually generate an internal sequence of reasoning and analysis in natural language to solve these complex tasks.
It's using its LLM backbone for chain of thought reasoning, but for physical output.
Exactly.
Okay, let's walk through that with a laundry sorting example, because that really clarifies the multi-level thinking that goes way beyond simple sensor-to-motor control.
Certainly. So the robot is told, sort my laundry by color. The process isn't instant. It's segmented by the planner.
Okay, what's step one?
First, the planner reasons at the semantic and logical level. It thinks something like, okay, sorting by color means separating white clothes from colored clothes. I'll use the white bin for whites and the black bin for all the non-whites. That's the goal definition.
Got it.
Second, it reasons about the current state and the next major step. I see a red sweater. The plan says the red sweater must go into the black bin. I need to pick up the red sweater.
Simple enough.
But third, and this is the crucial part, it uses its internal language model for self-critique and low-level planning. It might generate a thought like, the sweater is partially under a pillow. I should probably move the pillow slightly before I try to grab it to make sure I get a clear grip.
Or I need to approach from this angle so I don't bump into the laundry basket.
Precisely. So the final action is filtered through all these layers of natural language checks. It ensures the behavior is robust and not just based on one single, potentially wrong policy output. It really reduces the black box problem.
Yeah, that makes it so much more transparent and robust. And this whole foundation, this VLA framework, has led to what you said is one of the most exciting results, cross-embodiment learning.
Yes.
This is the concept that really signals a fundamental shift. It suggests that all those years of painful hardware learning might finally be paying off efficiently. So what does cross-embodiment learning let these systems do?
It means the software, the intelligence, is essentially hardware agnostic.
Yeah.
The skills learned and developed on one type of robot can instantly and effectively transfer across completely different physical bodies.
That's a huge deal.
Imagine the engineering nightmare this solves. Traditionally, if you taught a task to a mobile robot on wheels, you'd have to completely retrain it or do significant adjustments to teach that same task to, say, a stationary two-armed robot.
But now the LLM is the central brain, and the VLA executor is like a universal translator for motion.
That's a great way to think about it. DeepMind saw that tasks that were only shown to one type of robot, like the Eloha 2, which is a small mobile manipulator, those same skills also just work on entirely different platforms, like the Aptronic Apollo humanoid robot or the specialized two-armed Franca robot. What's transferring isn't just a set of joint angles, it's the high-level semantic policy, the understanding of the task, which the VLA then translates into the unique motor signals for that specific body.
That is the major leap. The intelligence can scale across multiple bodies.
That's the path to truly general-purpose robotic agents.
Okay, so the Gemini architecture solved the cognitive problem by letting the LLM do the planning. But we established that the biggest bottleneck for embodied AI is still the scarcity of real-world physical data.
Right.
Even the smartest robot in the world still needs millions of real-world interactions. So how do you scale data collection without hiring millions of humans to teleoperate these things?
The answer is AutoRT, which stands for Autonomous Robotic Agent Orchestration. AutoRT is DeepMind's system designed specifically to conquer that physical data scarcity problem. It does it by orchestrating entire fleets of robots to collect data in completely new real-world scenarios with minimal human supervision. It flips the whole data collection paradigm from being human-driven to being AI-driven.
So instead of a person manually moving a robot through 1,000 boring structured tasks in a clean lab somewhere,
Right.
they use AI to dynamically generate brand new tasks and then run them in chaotic real-world places like offices.
That's the genius of it. It's the scaling solution for physical data. And the process leverages the complementary strengths of the VLM for perception and the LLM for generating instructions.
Let's break down that loop. How does it work?
So the robot starts by exploring a completely unknown environment. Let's say a new floor in an office building or a cluttered kitchen. It just samples a random location near some objects.
Okay.
Step 1 is VLM perception and scene understanding. The robot uses its vision language models to look around and describe the scene. It identifies all the objects it can reach and what their properties are. It generates a detailed list. I see a bar of soap, a napkin, a snack wrapper, a cleaning cloth, and a sponge.
And crucially, it's not just noting what the object is, but where it is and what it might be used for. It's affordances.
Exactly. That detailed description then feeds directly into step 2, LLM instruction generation.
The brain kicks in.
The large language model is prompted to propose diverse, complex, and totally novel instructions for the robots to perform using the items it just identified. And the prompt gives it critical guidance. It suggests tasks that require complex, creative, precise, and dexterous motions.
So it's explicitly told to avoid boring, repetitive pick-and-place actions.
Exactly.
But wait, how does the LLM ensure novelty? Doesn't a model like that just tend to suggest tasks it's already seen in its training data?
That's a really sharp point, and DeepMind engineered a way around it. The LLM is prompted using techniques kind of like few-shot prompting, but with a focus on diversity metrics. It's told to generate instructions that combine the identified objects in new ways or require action sequences it hasn't been explicitly trained on.
Could you give an example?
Sure. If it sees a cup and a tissue, instead of just generating pick up the cup, it might generate something like use the tissue to lightly dust the rim of the cup and then place it upside down on the shelf.
Ah, so it's constantly pushing the robot into exploring these more complex real-world interactions.
That's how you solve the generalization problem that killed the Everyday Robots project.
So what kind of scale did they achieve with this? How effective was it?
The scale is what justifies the whole approach. Over 7 months, DeepMind deployed the AutoArt system across a fleet of over 20 different mobile manipulator robots,
20 robots.
all running in 4 different office buildings. And this effort resulted in the collection of 77,000 real-world robotic trials, or episodes, a massive leap in speed compared to the old ways.
And this wasn't fully autonomous, right? It was a hybrid approach. Why is that specific model so important for scaling?
Because fully autonomous operation in a busy office with people walking around is still way too dangerous and unreliable. The hybrid approach, where you mix autonomous policies for simple tasks with minimal human teleoperation for complex failures or high-risk moments, that's what scales efficiently.
So the human isn't a pilot anymore.
Exactly. The data showed one human supervisor could effectively oversee 3 to 5 mobile manipulators at the same time. The human becomes an orchestrator and a safety monitor. They only intervene when the robot flags uncertainty or a potential risk.
That maximizes uptime and data collection.
Massively.
But, I mean, when you have fleets of robots autonomously running around office buildings, proposing their own goals, trying out novel tasks,
Yep.
safety is no longer optional. It becomes the #1 engineering constraint.
It has to be.
So how did AutoArt build in the guardrails for this?
This is the critical and really the non-trivial engineering breakthrough. They implemented the robot constitution.
Robot constitution.
Yeah, and it draws direct inspiration from the constitutional AI approach that was developed by Anthropic. DeepMind prompts the underlying LLM, the one generating the tasks, with a comprehensive list of rules that strictly govern the robot's goal generation and its subsequent behavior.
So it's not a physical kill switch or a hardware cage. It's a semantic safeguard built into the language model's own reasoning that stops the robot from even considering a dangerous or infeasible task in the first place.
Precisely. You're leveraging the LLM's greatest strength, instruction, following, and reasoning to align the robot's goals with human safety values before the action even starts. And the rules are divided into 3 very specific categories.
Okay, let's break those down. The first set is pretty classic, right?
Yes, the foundational rules. They're heavily inspired by Isaac Asimov's 3 laws of robotics, but, adapted for the real world.
Okay.
First, the robot may not injure a human. Second, it must protect its own existence, so prevent damage to itself. And third, it must obey human orders unless that conflicts with the first 2 laws. And the priority is key.
How so?
Self-preservation is a higher priority than human obedience if the command is physically dangerous to the robot itself. That ensures the hardware stays operational and contained.
Makes sense. Okay, then you have rules based on the robot's actual limitations.
That's the second set. Safety rules. These are instructions that describe unsafe tasks based on current tech. The rules explicitly tell the task generator, do not generate tasks involving humans, animals, or any living things.
Right.
Do not interact with dangerous objects like a knife or scissors or any sharp edge, and do not interact with electrical items like a plugged-in tablet or a power cord.
Very clear. And the third category?
The third is the embodiment rules. These are crucial for feasibility, not just safety. They detail the current physical limits of the hardware. So the prompt might include rules like, this robot only has 1 arm, so it can't do tasks requiring 2 arms. Or this robot shall not try to lift objects heavier than a hardcover book.
Or don't try to go up the stairs.
Do not attempt to traverse stairs as your mobile base is limited to flat surfaces.
Exactly. Okay, that all sounds incredibly effective on paper. But did this constitutional prompting actually work? Did it make a measurable difference in safety out in the wild?
The results were dramatic. They were completely validating. DeepMind tested this using deliberately adversarial scenes.
You mean they set up environments with dangerous stuff just lying around?
Exactly. Environments set up with multiple sharp objects, power cords, things the robot should absolutely avoid. And without the constitutional prompt, the rate of the AI generating safe and feasible tasks was shockingly low, only 18%.
Less than 1 in 5 tasks it came up with in a messy room were safe or even possible. That's terrifying.
And that's exactly why autonomous data collection was a non-starter before. But
with the Constitution.
when the robot constitution was rigorously included in the LLM prompt, the rate of generating safe and valid tasks jumped all the way up to 83%.
Wow. From 18 to 83%.
And it gets better. The system has another safety layer they call affordance filtering. This is where the LLM does a self-critiquing step. It reviews its own proposed tasks against the 3 sets of rules.
It checks its own work.
It runs an internal safety check, yes. And that brings the overall rate of valid tasks generated up to an impressive 93%. This multi-layered approach is the cornerstone that makes large-scale, real-world data collection finally feasible and safe.
So Otter T and the Gemini architecture, they've clearly positioned Google DeepMind as a leader in the cognitive side of this, the brain. But as we look across the whole industry, they are not alone.
Not at all.
As this tech matures, we are seeing this fierce, competitive ecosystem emerge, and each major player is taking a pretty distinct strategic path. Let's look at the core technical conflict first. Specifically, how these robots translate high-level commands into actual physical motion.
This is the engine room challenge. It's the fundamental conflict in how control policies are engineered. And the debate right now is really centered between discrete or tokenized control and continuous control.
Okay, I think we need to dive into that technical difference. Explain how tokenization works for action control.
So the discrete approach, which was foundational to earlier models like Google's RT2, it treats physical actions like a joint angle or a grip or force. It treats them like language tokens.
Like words in a sentence.
Exactly. It takes the continuous range of motion and it breaks it down, it discretizes it into a finite vocabulary. So instead of 100 possible joint angles, the model might only have 20 tokenized options to choose from.
Why do that? It seems less precise.
The reason is purely strategic. It makes the physical control layer look exactly like the text layer. That simplifies the integration with the massive language backbone of the VLA model. It lets the robot immediately leverage the huge generalization power of the LLM.
So the robot is speaking the same language internally, whether it's planning a task or moving a joint, but there has to be a cost to that simplification.
Significant technical cost. First, you get what's called quantization error. When you map a smooth, continuous movement onto discrete steps, you lose fidelity. That reduces precision and dexterity. You might not be able to do a really smooth, delicate grasp.
Okay.
And second, and this is more important for the future of humanoids, this approach struggles to scale efficiently to systems with high degrees of freedom, or DOOF.
Like a human hand.
Like a human hand with dozens of complex joints. Modeling that kind of articulate movement with tokens just becomes computationally prohibitive and really error-prone.
Which naturally leads competitors who are prioritizing dexterity and precision to lean heavily into continuous control.
Exactly. Systems used by leading rivals like Figure AI's Helix model, they use continuous control signals. They output precise, real-time values for joint angles, velocities, and torques. This approach inherently offers much higher dexterity, surgical precision, and it scales much better for these high-DOF humanoids, which is why Figure's demos look so fluid.
There's a trade-off.
A huge trade-off. Continuous control requires far more specialized, low-level policy training and optimization. It's much harder to graft the LLM knowledge onto it. The whole control scheme is inherently more complex and slower to develop generalized policies for.
So it sounds like DeepMind is optimizing for cognitive generalization and the scale of data collection, and they're accepting some loss in physical fidelity to get there, whereas Figure is optimizing for physical fidelity and dexterity. And they're accepting the complexity of all that specialized policy training.
That is the perfect summary of the current strategic split. We can really compare the three major strategic vectors because they're all tackling this embodiment challenge in fundamentally different ways.
So you have DeepMind.
DeepMind, their strategy is all about maximizing cognitive scale, deploying that decoupled agentic architecture, and crucially, driving real-world data diversity with Otter T. They are the AI brain trust. They believe the brain has to scale first.
Then you have Figure AI, who seems to be the fastest mover in the actual humanoid space.
Figure AI is the exemplar of the hardware-software co-design approach. They are laser-focused on the humanoid form factor, which they believe is the best universal tool for human environments. Their Helix model prioritizes ultra-low latency, high-dexterity performance using that specialized continuous control.
And we see that in their demos.
Yeah.
The humanoids handling fragile groceries, smoothly closing drawers without being told how. It's real-time physical improvisation.
And their goal is commercial readiness. They're targeting warehouse and logistics work, at least initially.
And finally, there's the third strategic player, NVIDIA, who is kind of solving the data problem by sidestepping the real world entirely.
NVIDIA is positioning itself not as a direct competitor in hardware or cognitive architecture, but as the indispensable infrastructure platform for everybody else.
The picks and shovels.
Exactly. With their GR00T Dreams blueprint, which is founded on these Cosmos World Foundation models, they aim to bypass the physical data bottleneck completely by generating massive amounts of high-fidelity synthetic data.
So DeepMind is saying, let's automate the collection of rare, perfect diamonds in a messy real-world mine. And NVIDIA is saying, let's skip the mine and just 3D print perfect diamonds in a sterile digital lab.
That analogy perfectly captures the essence of the economic conflict. NVIDIA's platform, which is built around simulation environments like Omniverse, it allows developers to create training data super rapidly from minimal input. It could accelerate R&D from months down to hours.
But the age-old problem with synthetic data has always been the reality gap. How do you make sure data generated in a perfect simulation is actually useful for a real robot dealing with scuffs and scratches and real-world friction?
That's where a technique called domain randomization comes in. NVIDIA's whole value proposition relies on this. Instead of trying for perfect photorealism in the simulation, they intentionally randomize every conceivable parameter to the extreme.
Like what?
Lighting, friction coefficients, object textures, gravity, camera noise, even cable slack. The idea is that if the AI policy learns to succeed under infinite variations in the simulation, it becomes robust enough to handle the inevitable chaos of reality. It makes the synthetic data transferable.
That is a brilliant way to weaponize chaos for training. NVIDIA's strategy, then, is to accelerate the R&D pipeline for all the hardware players, and in doing so, establish themselves as the core platform for future robot intelligence, no matter who wins the hardware race.
It creates a really powerful flywheel. The strategic difference between DeepMind's AutoOrt, which is about real-world scale, and NVIDIA's synthetic data engine is arguably the central economic conflict that's going to determine the pace of physical AI deployment globally.
So looking beyond the technical competition, what does the market trajectory suggest for, consumer adoption? When are these things actually going to be in our homes, moving beyond industrial warehouses and R&D labs?
Market analysis suggests this acceleration is tangible. The LLMs and robotics market is expected to increase by something like $12 billion between 2025 and 2029.
That's a huge jump.
It's accelerating at a compound annual growth rate of over 38%. And while industrial robotics still holds the largest market share, precise factory arms,
Right.
the major growth is coming from service robotics, autonomous vehicles, and, critically, humanoid robots designed for general environments.
So what's the consensus timeline? Are we talking about rich buyers adopting them first, kind of like early electric vehicles?
That is absolutely the consensus speculation from the source material. Experts project consumer-grade robots could arrive in perhaps 5 to 10 years, though, limited availability to rich early adopters paying $100,000 or maybe even $20,000, that could happen sooner.
And those initial models will probably be slow, need recharging all the time, not nearly as capable as the demos.
Of course. But just like with any high-end consumer tech, those early buyers are the ones who will fund the refinement cycle. The expectation is that they'll follow the same trajectory as personal computers or cars. They'll start as a luxury item and then rapidly become feature-driven consumer products.
With multiple companies competing fiercely on specific capabilities and price.
And the cost comes down rapidly as volume and software efficiency go up.
And the really unique factor here is that the intelligence is constantly upgradable.
Yes, that's the game changer. The underlying intelligence, the Gemini software, it can be updated remotely over the air. A robot you buy today might learn a dozen new chores in 3 months from an update. That constantly lowers the effective cost of ownership and the barrier to entry over time.
The bottleneck is shifting from can the robot think to can the robot be safe, ethical, and reliable enough for mass deployment.
Exactly.
This has been an incredibly detailed look at a foundational challenge. We started this deep dive understanding the 7-year frustration of Google's Everyday Robots mission, which really proved that physical data scarcity was a technological wall.
A huge wall.
But they learned that hard lesson and pivoted successfully to this sophisticated agentic architecture.
Absolutely. That failure led directly to the breakthrough of Gemini Robotics 1.5, which bypasses the slow learning problem by leveraging the massive cognitive scale of LLMs. This cognitive brain is then fed the physical data it needs at scale via AutoOrt, which orchestrates these robot fleets using constitutional rules to ensure both safety and novelty.
The whole system is just accelerating the movement from theoretical intelligence to practical physical agency.
It is.
And as this capability accelerates, we've established that safety is no longer an afterthought. It's the primary engineering priority, enforced across multiple layers.
It has to be. DeepMind uses a really holistic approach. It encompasses physical safety through low-level hardware controllers, operational safety through fleet management and auto-T, and critically, semantic safety.
Semantic safety.
Ensuring the VLA model understands that a potential action, like trying to pick up a knife or interacting with a child, is contextually and inherently dangerous. They're even releasing data sets like ASIMO to help the whole community evaluate and improve semantic safety in these systems.
The regulatory landscape is trying, at least, to keep pace with these massive leaps in autonomous capability.
Yes, particularly in Europe. The European Union's reforms, especially the machinery regulation, which starts taking effect in 2027, are pretty revolutionary here. They define strict autonomy thresholds,
Meaning what?
meaning machines that demonstrate self-evolving behavior through experience, which is exactly what Otter-T and Gemini Robotics do, they face much enhanced conformity assessments. They have to provide documented safety proofs for future learned states, not just their current programming.
It's a big deal.
And the regulation also mandates lifetime cybersecurity responsibility for connected robots and requires collaborative risk mapping for human-robot workspaces. The framework is rapidly trying to mandate safety and accountability.
So we've tracked the technical challenge, the data challenge, and now the safety challenge. But there's one final thought that grounds this whole conversation in the long-term human element. This raises a really important question. When robots are governed not by rigid code, but by an internal AI-generated constitution, and they are constantly collecting data to improve their policies autonomously, how do we ensure that small, seemingly safe actions don't inadvertently lead to complex behavior that is fundamentally misaligned with human values down the line? Especially if the underlying deep learning process generating those policies remains somewhat opaque.
Right.
The work to mitigate the inevitable downsides of this incredible innovation, ensuring that Constitution is robust enough for anything, is just as important as the innovation itself.